Episode 2, Mars, the Big Picture. Why does Mars look the way it does? In the last episode, I talked about why I started the Mars Explorer. But before we follow Curiosity across Gale Crater, explore the ancient delta at Jezero, or examine individual rocks photographed by Perseverance, we need to step back. Way back. Because from orbit, Mars tells an extraordinary story. It is a planet divided almost in two. It has the largest volcano in the solar system, a canyon system that would stretch across much of the United States, one of the largest impact basins in the solar system, and polar caps that preserve a record of a changing Martian climate. So before we go exploring on the ground, let's take a tour of Mars from above. And let's start with how we first saw it, seeing Mars for the first time. For centuries, almost everything we knew about the surface of Mars came through telescopes on Earth. Astronomers saw light and dark regions. They saw polar caps changing with the seasons. And some observers believed they could see long, straight lines crossing the surface, the famous Martian canals. That image of Mars persisted well into the 20th century. Then, in 1965, Mariner 4 flew past Mars. For the first time, a spacecraft photographed the Martian surface up close. The pictures were crude by today's standards. They covered only a tiny portion of the planet. But what they showed was revolutionary. Craters. Lots of them. Instead of an Earth-like world crossed by canals, Mariner revealed something that looked, at least in those first images, more like the Moon. But there was a problem. Mariner had seen only a very small part of Mars. It had answered some questions while creating many more. Later, Mariner missions, and eventually the Viking orbiters, began revealing that Mars was far more complicated than those first photographs suggested. And then, in 1976, Viking changed our perspective again. Viking 1 and Viking 2 didn't just orbit Mars, they landed on it. For the first time, we could stand, at least through the eyes of a spacecraft, on the surface of another planet and look toward the horizon. A rocky plain, a reddish sky, boulders scattered across the landscape. Mars was no longer just an object in the night sky. It had become a place. And during the decades that followed, increasingly sophisticated orbiters began mapping that place in extraordinary detail. Today, spacecraft such as Mars Reconnaissance Orbiter can show us individual boulders and layers of rock from hundreds of kilometers above the surface. But sometimes the best way to understand Mars isn't to zoom in. It's to zoom out, a planet divided in two. One of the first things you notice on a topographic map of Mars is that the planet seems almost divided into two different worlds. Much of the northern hemisphere consists of relatively smooth, low-lying plains. The southern hemisphere is generally higher, rougher, and covered with ancient impact craters. The difference in elevation between these regions can be several kilometers. Planetary scientists call this the Martian hemispheric dichotomy. And we still don't know exactly why it exists. It could be the result of processes deep inside early Mars, or an enormous impact may have reshaped much of the northern hemisphere. There are other hypotheses as well. What we do know is that the southern highlands preserve some of the oldest terrain on the planet, while much of the northern surface has been resurfaced. And that raises a fascinating question. If ancient Mars once had an ocean, the northern lowlands are one of the places where much of that water may have collected. We'll return to that in a future episode. But now let's move toward the equator, and one of the most extraordinary geological regions on any planet. Tharsis. Rising above the surrounding terrain is an enormous region called Tharsis. Calling Tharsis a mountain doesn't really capture its scale. It is a vast volcanic plateau thousands of kilometers across. Sitting on it are some of the largest volcanoes in the solar system. and one of them towers above all the others: Olympus Mons. Olympus Mons is the largest known volcano in the solar system. It rises roughly 20 kilometers above the surrounding terrain. But perhaps even more impressive than its height is its width. Olympus Mons is approximately 600 kilometers across. If you stood on its lower slopes, you wouldn't see a mountain rising dramatically in front of you. The slope is so gradual, and the volcano so enormous, that much of it would extend beyond the horizon. Why could a volcano grow this large on Mars? Part of the answer may be something Mars apparently doesn't have: Earth-like plate tectonics. On Earth, tectonic plates move across volcanic hotspots. That movement can produce chains of volcanoes, like the Hawaiian Islands. But on Mars, the crust remained relatively stationary. A volcanic source could therefore continue erupting in approximately the same location for an extraordinarily long time. And the growth of Tharsis may have affected much more than the volcanoes themselves, because immediately to the east is one of Mars's most recognizable features: Valles Marineris. Valles Marineris is a canyon system approximately 4,000 kilometers long. In places, it is hundreds of kilometers wide and several kilometers deep. It is tempting to call it the Grand Canyon of Mars. But that comparison can be misleading. The Grand Canyon was carved primarily by the Colorado River. Valles Marineris probably wasn't. The leading explanation is that the immense stresses associated with the rise of Tharsis stretched and fractured the Martian crust. Large blocks of crust dropped downward along faults, creating an enormous rift system. Water, landslides, and erosion modified the canyon later, but they probably didn't create the original structure. So Valles Marineris may be telling us something much larger than the history of a canyon. It may preserve evidence of stresses that once acted across a significant portion of the Martian crust. We'll take a much closer look at that story in a future episode. Now let's travel south. Hellas Planitia. Here we encounter something completely different: a vast circular depression more than 2,000 kilometers across. This is Hellas Planitia, or the Hellas Basin. Unlike Valles Marineris, we have a very good idea how Hellas began. Something enormous hit Mars. More than 4 billion years ago, an asteroid, or possibly another large impactor, struck the southern hemisphere with enough energy to excavate one of the largest impact basins in the solar system. The floor of Hellas is also one of the lowest places on Mars, and because it's so deep, the atmospheric pressure there is higher than across much of the planet. But Hellas raises another question: what effect could an impact this large have had on the rest of Mars? Could it have affected the crust? The mantle? Volcanism elsewhere on the planet? Those questions take us into some fascinating and much less certain territory. And we'll explore them separately. The poles. Now let's travel to the top and bottom of the planet. Mars has polar caps that expand and contract with the seasons. But these aren't simply frozen versions of Earth's polar regions. They contain enormous deposits of water ice, along with seasonal carbon dioxide frost. Perhaps even more interesting are the layers. Mars's polar deposits contain layer upon layer of ice and dust. Those layers may preserve a record of changes in Martian climate stretching back millions of years. In some ways, they're like the ice cores scientists drill in Antarctica and Greenland, except this climate record is sitting on another planet. Understanding those layers could help us answer one of the biggest questions about modern Mars. How did the planet's climate change over time? One planet, many stories. So step back again and look at the entire planet. Ancient cratered southern highlands, smooth northern lowlands, the immense volcanic province of Tharsis, Olympus Mons towering above it, Valles Marineris cutting across the landscape, the enormous Hellas Impact Basin, and frozen polar regions recording changes in climate. These aren't just landmarks on a map, they're evidence. Each one contains part of the story of how Mars became the planet we see today. And over the next several episodes, we're going to explore them one at a time. We'll ask how they formed, what evidence scientists use to reconstruct their history, which explanations are well supported, which are still debated, and what remains unknown. Because before we can understand what curiosity or perseverance sees in a single rock, we need to understand the planet that created that rock. That's the bigger picture. And now that we have the map, we can start exploring. I'm the Mars Explorer. I'll see you in the next episode.